Okay, my name is Rahul, and I work for a hedge fund called Co2 Management. So this is really my side project. This is not what I work on a daily basis. So since I work for a hedge fund, I can't really talk about my work. So what I do every year is like I take some random project and spend a couple of months and like create like a brand new library or do something cool with it. So that's what I did with probabilistic programming as well. So my goal is just to teach you like what probabilistic programming is. So there have been like 3 talks where people talked about like what they're doing with their libraries. So I want to concentrate a little bit on like what the probabilistic programming is, and then I'll talk about the library that I wrote. So before we start, let's do a small thought experiment. Hopefully this will give you enough intuition on what probabilistic programming is. So let's do that. So how many of you have seen this movie called Limitless? Please raise your hands. Don't be shy. Okay. So for the people who haven't seen this, so there is this drug called NZT. And if you take this drug, 2 things can happen. So you can either become the smartest person in the world, and you can do like all crazy things, or you can have like really bad side effects, and you might even die from it. So you want to be really sure before you want to take such a decision, right? So the pharmaceutical company that made this drug, they collected like a lot of data points around this. So the blue points that you see here are the ones like people who took the drug and survived and hopefully became smarter people. And the red ones are the ones where like people had like really bad side effects, or they even probably died from it. So what are we going to do with this data now? So obviously we are going to train a model, and these days everything is deep learning. So we are going to train a deep learning model, and as Google says, you don't even need a PhD to do that. And let's see what the accuracy would be with such a model. Yay, we got 100% accuracy. So what this is showing is anything that is above the curve, it is purely safe. So and whatever is below the curve is a dangerous zone, and you don't want to take the drug if you are in this zone. So this is too good to be true, right? This is like a perfect model. So you have like a deep net that essentially classified, and it actually bent itself and classified perfectly. So now you get excited with this model and say, hey, pharmaceutical company, can I also please try this drug? This is like I want to be a really smart person, and can you help me with it? And then they say, hey, yeah, okay, so I'll take your blood work, and they take your features from your blood work, and they place you there at this black point. So my question to you is, like, if you were this black point, like, would you take this drug? So this is well above the curve, right? So how many would take it? Just 2? Come on, guys. Not Avi. Okay. So it seems like a no-brainer to me, because like it is well above the curve, and the model says it is 100% accurate, that accurately classified that this is a blue thing. And let's see what happened to that guy who took the drug. Boom, he died. Whoever took the drug, they died, because like we can't never be sure like about the data that we haven't seen. But yet, like the models that we do today, they give you like 100% confidence about like some things that we haven't seen before. So that is the problem we are trying to address here. So let's do another round. So you already fixed your model. You have 100% accuracy. Now, if you are this black point, would you take it again? No? You guys are getting smarter now. You don't even need a pill. Okay, so as you expect, so that's not the right model. So this turns out to be the right model, and we were bad twice, and this could be very costly if your life is depending on it. So that's exactly what we are trying to solve here with probabilistic programming. So what happened here? So if you look at the models that we had before, they're like 100% accurate, and they totally separated the blue dots from the red dots, right? So we have one model here, second model, and the third model. And every time, like we said, like 100% accurate, but that turned out to be not true. So essentially, what we want to do is like we want to make a confident decision. And so if you ever have to take a decision where your life depends on it, you want to be really sure. So that's what probabilistic programming will help you with. So how do we solve this problem? So one idea that came to my mind is, so like we saw 3 models, and one idea is like instead of one model, one deep learning model, like can we have like three models or a bunch of models? So that's what we see here. So now instead of one model, we got 3 models. And let's say like we're trying to predict, like we want to know the confidence of these 3 points. So for the P1, so the confidence of the probability of P1 being red is 2 out of 3 because there are 3 models here. And 2 of the models say, hey, it's P1 should be red. So out of 3 models, 2 are saying it's red. So that's why the probability of P1 being red is 2 out of 3. And the same thing with P2. So one of the models, the pink one, is saying, hey, it should be in the red zone. So that's why the probability of P2 being red is 1 out of 3. And all the 3 models are agreeing on P3, and it is highly confident about P3. And then, so if you were to take a pill, being a P3 or P1, you would have like more confidence with P3 than P1, right? Because the probability of P3 being red is almost close to 0. And the next idea is like, why stop at like 3 models or few models? Why not generate all the models? But there are, as you can imagine, there are like infinite curves that can fit this. But there is a solution to it. So essentially, if you model it as like probabilistic with continuous probability distributions, you essentially get a surface. So earlier what we saw was like we saw a few curves, but rather than that, like if you model your program probabilistically, then you'll get a probability surface, and this surface is saying that, hey, like wherever it is dark, it is like highly uncertain, and the areas where it is light, it is very certain about it. So essentially, you have like infinite ways to do it. So let's see what we are proposing here. All right. So this is where we started before this talk. So this is how like all our models are working as of today. So we have like one uncertainty curve, and we also have like one answer for prediction. So it could be safe or deadly, and from here we want to go here. So instead of prediction being like one answer, you want to get a range of answers. So that's what the prediction is saying. And for the uncertainty curve, instead of getting one curve, you want to get a probability space. Is that clear so far? Okay, cool. Now let's look at models with and without the probability. So I got these slides from Eric Ma. He gave an awesome presentation on like how the models look like with and without the probability. So you should check it out. And Eric Ma, wherever you are, a big shout out for you. Okay, so let's look at a linear regression model. So the idea of linear regression is you have a bunch of points and you want to fit a line through those points, right? So essentially what we are computing is that red point and the cyan point. The red one is the slope of the line, and the cyan one is the y-intercept. Okay, so this is like plain modeling 101, and essentially what you get is like given a point, you get an answer back, which is the y, and all these are points, right? So however, like as we discussed before, you don't want one answer, you want a distribution of answers, right? So my question to you is like, what do you do with these weights so that you get a distribution back at the end? Can anyone take a guess? No guesses? Avi, you know the answer. So essentially, instead of looking at these as points, you have to make them probability distributions. And when you multiply a point with a probability distribution, you get a probability distribution at the end. So let's take a look at that. So all probabilistic modeling does is, instead of having like points as your answers, like as your parameters, you have probability distributions as your parameters. So that's essentially the crux of probabilistic programming. And let's see like how a deep learning model would look like with and without the probability. So deep learning, there is nothing deep about it. It is a bunch of function compositions with a bunch of matrix operations. So essentially, a deep learning model like that we saw before looks like this. So it has a bunch of parameters and a bunch of function compositions. And if you were to make this deep learning model a probabilistic deep learning model, you just have to make these parameters probability distributions. So essentially, what we are doing is from this state, we're going to this state. That's essentially probabilistic programming. Is that clear so far? Yeah?
Well,
yeah.
So I find Eric's slides misleading here because I
Yeah.
think that it implies that the distributions for each of the parameters are independent.
Right.
Right?
Yeah.
In fact, what you have is one very high dimensional distribution.
That's
and
also true.
Correlations between the parameters.
Yeah.
I think that's important.
Yeah, yeah. So how do we address that? Maybe we can talk offline. Yeah. Okay, so why there is so much hype today? So I feel like we are already doing good with the deep learning models, but as you saw before, like we are like so confident in areas where we shouldn't be so confident, right? So like the current research is saying that, hey, like instead of being like so much sure, like add uncertainty to your models. So that's what we are trying to fix here with probabilistic programming. And as you can see here, there are like many popular repos. Uber has Pyro, and PyMC3 is very popular in the Python community. And TensorFlow is also adding a bunch of commits to probability. They just started with it. So, however, like there is one common thing that is bad with all these repos. Not bad, but where we can do better. Can you guys take a guess?
They're all Python.
Exactly. Yeah. So obviously we want to do this in Scala, and if we were not doing it in Scala, like I wouldn't be talking here. So I created this library called proml. So if you are excited to work on probabilistic programming, you guys should check this out. And so let's do some. So let's see how we can do this in Scala. So let me talk a little bit about my library. So here proml is a probabilistic machine learning library that is written in Scala. And what I say here, it's purely functional. So what is purely functional? So any probabilistic machine learning library, it has to support distributions and samplers. So this is like the very core thing of any probabilistic machine learning library. And I made sure that like there are no side effects in these two things. So they all take an input of type A and give an output of type B, and there are no side effects. So this is the pure functional piece. And I say it is backend agnostic. What is a backend? So if you have to do some machine learning modeling, you have to choose your backend, which is like is it TensorFlow or Torch or MXNet or whatever, right? So, and whatever code that we are writing, it should be backend agnostic, because like the models that we are writing, they are not tied to like one particular backend. So they essentially, so how do we solve this problem, right? So we simply abstract this away with a type class. So this is what we learned from like Scala Z and cats, right? Essentially, we create like type classes to solve things that other libraries don't support. So what we do here, so we create a type class called backend, and you just create type instances for the backends that you have. So let's say, in my case, I created a backend for Breeze and one for TensorFlow. And all you need to do, if you have to change your model to switch from one backend to another backend, it's just one line of change. Isn't this amazing? So PyMC3 is a popular Python library, and they were tied to Theano, and Theano, they stopped their support, and they're spending almost a year to move away from Theano to TensorFlow, and we don't want to let that happen with our library. So you can simply abstract that away with a type class. So another type class that I provide here is the matrix Typesafe matrix operations. This is similar to what Tongfei is working on. Yeah.
How did you make the TensorFlow backend?
So I'm using a library called TensorFlow Scala.
Okay.
So it is a wrapper on top of that. So yesterday we saw this talk from Tongfei Chen where he talks about Typesafe matrix operations. But we have some libraries written in Scala today that does linear algebra, like Breeze, so which has no idea of what the dimensions are, right? So if you were to create a matrix, all it knows is it's a dense matrix of some data type. It could be int, boolean, or whatever. And the same thing with ND4S as well. So, and if you were to do some kind of matrix operations, while working on your deep learning models, you have no idea when it would be type safe or not. You can totally do some mistakes or typos as here. So for example, you have a matrix that is of n by 2, which is your x here, and you're doing a dot product with W1. If you made a typo, you want to get some nice error that says, hey, that is not possible. That's what you get with this library as well. And hopefully, going forward, I can probably work with Tongfei and get some concepts from him and include this in the library. So let's take a look at a few machine learning models. So let's go with linear regression. So the idea of so this is a model, right? So let me show you the data that I have. Oh, one thing that I also support in my library is the notebooks. So if you go to my library, we have some nice notebooks for a bunch of examples in there. And I think that is very crucial for our Scala community. I think this is one piece that we are missing in Scala, where we don't really care about UI. And if you were to give your library to some data scientist, and if you want him to do some machine learning or whatever, he's not going to use it because there is no way he can play with it without even seeing all these models. So you need to support some kind of UI, otherwise there is no point writing your library. And I think Rainier did a good job as well. I got some data points from them. So they use cplot. I'm actually using something similar. It's called evilplot.
Did you try to use Beaker?
Beaker?
Beaker.
No, I haven't.
It's a module, Scala module for Jupyter notebooks.
I see.
Works really good.
I see. Yeah, probably I can look at that after this. Okay, so having said that, let's look at a linear model. So essentially, what I did was I took a line and added some noise and plotted it here. So the actual y-intercept and slope are here. So the real slope is 2, and the intercept is -2. Okay, and I generated a bunch of points. And the idea is to train a probabilistic model on top of this. So let's look at how the probabilistic model works. So essentially, probabilistic modeling is nothing but Bayesian inference. And the way we do it is so essentially we want to get the posterior. So P of parameters given data. And this is nothing but likelihood times prior by P of data. And what is P of data? This is some nasty thing that we don't want to compute. It's really hard that we can't even compute, right? So essentially, so then we use this technique called MCMC, Monte Carlo Markov chain. that says that like, hey, like if you do some random walks in this probabilistic space and collect some data points along the way, so this p of x gets cancelled. And I can talk about it for like almost an hour. It gets deeper than this. But essentially, just believe me that this is what it is. So this p of x get cancelled, and you get samples from your probability distributions along the way. So let's take a look at what MCMC is. So if you go look for MCMC, there is like, you get like so many definitions. And like one of the things that Wikipedia says is this big paragraph, which I don't clearly understand. So my version of MCMC is, you start at a point in your probability space, right? And you take some random walks. And these random walks are biased towards the high probability areas, okay? And what you do is like, while you're doing these random walks, you collect some data points along the way. And that's it. That's what MCMC is. And let's take a look at some animation which will make it clear. So let's say you're at this point, right? And you're jumping like randomly, but this jump is like biased towards the high probability area. So this is a high probability area, and you're jumping towards that. And it also does walk randomly, so you also get to these points where it's not like really high probable. So the number of points that you will collect from this area will be smaller. And if you do this like million number of times, you get a probability distribution of your like slope and y-intercept, and this is your like samples that you find here. So this is the crux of MCMC. So right now my library only supports Metropolis Hastings, and there are like some huge breakthroughs in this space. So I think the latest one is ADVI sampler, and I'm planning to add that sometime soon. Okay, let's back.
Switch it Hamiltonian MC.
So I thought like, hey, like I have like a real basic version of MCMC, and if I can do like the most complex one or the best one, that's all I need. So yeah, since I just started working on this like a month ago, so I just came up with this Metropolis Hastings. And this Metropolis Hastings algorithm is like 3 lines of code. You can check it out in my library. Okay, so let's get to the model now. So all we are saying is, so we have this likelihood and we have this prior. We're trying to get rid of this P of data. And if you look at the model, it's a trait. All you have to do is like implement these 4 methods. What are these 4 methods? One is proposal. So the proposal is nothing but, so this is the MCMC piece where you're at a point and you're jumping somewhere, right? So it'll give you the proposal of like where should you jump. So that's your proposal. And log prior is P of theta, and so the likelihood is computed in the model. And you are starting at some point. So that is your like prior assumption. So in this case, we started at like some, so let's see where we started at. So in this example that I'm giving, I started at like slope being 100 instead of 2, and minus 10 instead of minus 2. So it could be totally random. So that's your prior assumption. And you have this model that says, hey, y equals to mx plus c kind of thing, right? So that's your model, a single line of model, that's it. And so given this model, you're providing this sampler that I talked about before, the Metropolis Hastings. And here you say, hey, like generate like 20,000 samples and just burn the 15,000. It's probably more clear if you work on it. So essentially you throw out the first few thousand ones so that like you don't get like bad data from it. And now let's look at like what it computed. So in a model without the probability distributions, you get a single answer, which is exactly what we predicted, like 2 and minus 2 here. But here with the probabilistic machine learning model, you're getting a distribution, which is concentrated towards the like the real values, but it will also give you the uncertainty of what the things could be. So Let's do the same thing with Bayesian deep learning. So before we get to that, so let me concentrate a little bit. So in the case of linear regression, all we computed is 2 variables, right? Nothing much. But you can easily extend this to like a Bayesian deep learning model. So here, every edge you see here is a weight. And as you can see here, there are probably 30 or 40 weights here. So essentially, I'm doing the same example that I did before in my slides. So I want to separate out the green ones from the red dots. So which I do here in this case with the deep net with probabilistic models. And as you can see here, I have all these matrices that are completely type safe. So this is the type class that I was talking about before. And all it takes is either some kind of dense matrix. It could be either a TensorFlow matrix or it could be Breeze matrix. It doesn't matter. So that is abstracted away. And now this is your neural network model. Essentially, we are doing the same thing. So you have a proposal function, and you have the log priors, which is p of theta, and you're starting with some prior assumptions, the same thing as the linear model, and all you're doing different is just this line, and this is your deep learning model, just one line. So let me show you how it looks like if I made a typo here. So hopefully, for some reason I can't make it bigger.
You can switch to the presentation mode.
Oh, yeah.
No, in IntelliJ there's view.
Oh. Anyways, I'll probably show it here. I think it's much better. So anyways, so if so this is your input, right? So this is of dimensions n by 2, and you're doing a dot product with W1, which is of type 2 by 5. And for some reason, you made a typo here, right? Instead of W1, you had W2. This will throw an error. So you will get an error in IntelliJ and say, hey, you're doing something stupid. And that's what we want to get from our compiler. And the same thing. So if you wanted, instead of Breeze, if you wanted to have a TensorFlow, all you do is one line of change, and that's it. So you get a TensorFlow model instead of a Breeze model. And that's what you get from all these things. So we are almost done here. So closing points. Thanks to Erikma for your slides. And if you find this interesting, come work for Kotu. So we do have a lot of back-end and front-end positions. And I'm happy to chat with you more if you are interested. And please start this repo. So it's not about you and me. I think this will help build the ecosystem. I think that is more important. Yeah.
The repo, we need to win against Python.
Yeah.
We need everybody to.
Yeah. Thank you so much. Hopefully we can be on the top.